Okay, so now we are going to code the robot maze problem. But before we code it, let's look back at our outline that we wrote for this function. So in our outline, we have the base case and the recursive cases, right? So if you remember, the problem was a robot was on the top left corner and is trying to make it back home. And to make it back home, there's a list of obstacles. Let me show you. Here it is. It's a little bit small, but as you can see, there's a robot, and then there are a bunch of X's, which are obstacles, and then you have to figure out how the robot can go back home. So you have to give it directions. So that's basically the question. Now, this is basically the solution already written out in terms of human language. So the base cases, which means the cases that are the most easy to solve, is if the robot is already home, then you just return the current solution that you already have, because the key to recursion and for backtracking in this problem is that you keep your solution on a parameter. And then your function doesn't really know what happened before, but if you pass in a parameter that has the current solution, like a list of directions, then you know that you could just return that solution. Anyways, so if the robot is already home, then you don't need to do anything. If the robot is out of bounds, then it's no solution because you can't go out of bounds. And then if the robot is on an X obstacle, that's also a no solution. So these are the base cases, the super easy ones. Now the recursive case, then how we do the recursive case is there are two options. Every time you are in a position, then you can do two things. You could either go right or you could go down. In case you're asking, what if on the right you have an obstacle? You're not allowed to move right. That is true, but it is handled by our base cases, right? Because once we realize our robot is out of bound or it's in an X obstacle, we'll just give it no solution. So it makes the code a lot cleaner, and you'll see why later on. So in the recursive case, we have solve for the subproblem if the robot goes right. And then here it says add right to your solution. So we will add right to our solution and then recurse and have a new position of our robot. So our robot is one position to the right now. And then we pass that to our recursive function. And then if it gives us no solution, then we backtrack by removing the right label to our solution and then trying to do the same thing but going down instead. So that's pretty much the recursive case. So just reading the recursive case, what are the states that we have to remember? Well, for recursion and backtracking functions, we have to pass information to the recursive function so that the function can work on this new state. Like for example, in Fibonacci, we needed the number n. That was basically our state. At which point of the Fibonacci numbers are we at, right? So for example, if you solve fib of 5, you have to first solve fib of 4 and fib of 3. So the 5 here, that is basically the state. And then later on, you pass on a state to the next function you call, which is Fibonacci, but you pass it the state number 4 and the state number 3, right? So these are the states, aka the parameters that we're gonna send to our function. So in this function, the robot maze problem, we're attempting to solve a maze. So the maze is actually constant throughout because it doesn't really change. But what's not constant is our robot's position, right? So we already have two so far here. Let's just remember this would be constant. So it doesn't change, but you could still pass it as a parameter and it's going to be constant throughout. And then the position of the robot, this is not constant. All right, so for example, if you pass in the position 0, 0, which means this position on the 0 row and 0 column one, or, like a position 1, 0, which could be right here. And then like position, let's see, 3, 3, 0, 1, 2, 3, 0, 1, 2, 3. It means here, that's the end state. So these are what positions are. This is the state that you have to pass into your function so that your function knows where your robot is. And then the solution, that's just the directions, so that your next function you're calling has to know what is your solution so far. So let's write so far. So they have to know what your solution is so far so they can build upon it and finally produce the correct solution. So why did I talk about states? Well, like again, I want it to be ingrained in your head that it's going to be the parameters that you will pass on to your own function. You have to give information for the recursive call of your functions. So now that we know we need a maze, the position of the robot, and the solution, we know the parameters. Now, what is the format of these parameters? Well, first we have to look at the question. So here's the question. We have print maze and solve maze. This is the function that you are going to write. And then print maze is just a helper that allows you to print the maze in a, I don't know, it's just a lot easier so I can show you what the maze looked like. So this is the maze. So as you can see, this is a list of characters where a dot means it's a valid path and an X means it's an obstacle and you cannot cross it. If we compare it to our original drawing, it's the same thing. As you can see here, it's kind of small, but it's basically the same thing. Here are all the dots and then these are the X's. It's the same thing, dot, 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 X, 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 X. So, okay, so this question decided to format it this way. And then the solution, they decided to format it in a list of characters where D means you're going down and R means you're going right. So for example, on this maze, we know that the solution is this path over here. So down, down, right, right, down, right, which is why you get the list D, D, R, R, D, R. All right, cool. So now we know. So let's just write this down so we don't forget. So this would be a list of list. And in the position, we could choose anything we want, but let's just give it a number for the position of the row. And then for the column, we'll also give it a number. All right, so that makes it a lot easier. You don't need any fancy data structures. And then the solution will be a list of characters. I'll just write lists of D's and R's, right? Because that's more precise. It's you go down or right. And then this is a list of dots and X's. All right, perfect. Okay, so now we know what parameters we want to pass in. So let's go straight to code now. So first, let's do an easy exercise just for warm up. Let's try to print the maze. Okay, so what do we want to do? We're just going to do a double loop. And then this double loop, it will print the double maze in a cooler format. All right, so for each row in the maze, what we want to do is we want to create a string. I'll just call it row print. So this is the string that you'll print. And then for each row, I want to look at each value. So this is kind of like each column. So for each value, I'm going to add the value to my row, which is the string that I'll print. And then I'll also add a space, a little white space, just to format it. And then I'll just print the whole row itself, and it will print it 4 times because I have 4 rows, and I don't need to return anything. Oops. All right, let's just delete this. So now let's try it out. We got maze. See, it's not very formatted very well. Even if we print maze, it won't work. But if we use our own function and we print the maze, this looks a lot better. So this looks exactly like what we had in our example. So if you see on the slide, as you see this robot and the maze looks the same. So now that we can print maze, the thing we have left to do is to solve the maze. Remember what I said about the parameters that you have to give in the parameter? However, here, there's only maze here. Why is there only maze? Well, it's because if there's a client or somebody is using our library and wants to call solve maze, you don't want them to put unnecessary parameters. You're the one that has to deal with it. So you can define something called maybe like a solve maze helper, which actually has all the parameters that you need, right? But the client or someone else that uses your function, they might not want to care about all the other states that they have to pass in, right? So which is why we're creating a function helper. So in some ways, this is kind of like the main function, and this is just a function wrapper so that they don't need to pass as many parameters as they need. So remember what we said? We said we wanted a maze. We want to pass in our solution, and we want to pass in the position. We'll call it position row and position column. All right, so now you have these parameters. Okay, let's try to solve it now. Let's go back to our slide and look at the base cases. So now that we have this outline, it's actually really easy to code it up because we already have the outline here and it tells us exactly how to code it. All right, let's start with the base cases. Is the robot already home? Okay, let's just write that down. So how would we know if the robot is already home or not? Well, first, we know that the home is at the corner, right? So for example, on this maze, on this little maze, the home is basically the corner, right? So what you want to do is get the size of your maze first, and then you know where the corner is. Let's do that. So first, what you want to do is you want to count the number of rows on this maze. So that's easy. You just take the length of the maze, which is actually a length of a list. And then to get the columns, we do the length of the maze and we just take the first row. And so we count how many columns there are. All right, perfect. So now you have the size of the maze. Get size of the maze. All right, so I'm gonna keep writing comments so that the code is clean. And then if ever people want to modify the code, it's a lot easier. So here we want to solve for base cases. Okay, so the first base case we're going to solve is that robot is already home. So robot is already home. Okay, so how do you know when a robot is home? Well, you want to know if its position is the bottom right corner. What is the bottom right corner? It is the number of row -1 and number of column -1, right? The reason why it's that is because it starts at 0. The index, it starts at 0. So for example, if there are 4 items here on a list, then it's 0, 1, 2, 3, right? And then the number of items here is 4, right? So let's say if the position of the row equal to the number of row -1, so that means it's on the last row, and the position of the column of my robot is the same as the number of column -1, which means it's at the last column, then, I don't have space anymore. But anyways, I'll return solution. Wait, let me move this a little bit so we can see. Okay, and then we just return solution, like our slide says, return current solution. Okay, we'll trust it for now. Is the robot out of bounds? Okay, and then if it's out of bounds, then I just write no solution, out of bounds. So how do we know if it's out of bounds? Well, if the position of the row is equal or greater than the number of row, because we know that this is actually the last row. So anything bigger than that, it means you're out of bound. Or position of column is greater than or equal to the number of column that exist. And then if that's the case, I'll return none. So what this function does is it'll just print nothing. If ever there's no solution, it'll print nothing. If there is a solution and you don't need to move, we'll return an empty list. Okay, so what about the next one? Is the robot on the next obstacle? If so, no solution. Is on an obstacle? This one should be easy. So how do you solve this? Then what you want to do is you want to check the maze at the position of the robot. So position row and position column. So that will give you a cell of the maze. And then you want to make sure that it is not an X. So if it is equal to an X, then you return none because that is not allowed, right? If it was a dot, then it means it was a valid state. So you continue. But if it's an X, then you return none because you're not allowed to do that. All right, so we're done with the base cases already. Let's do the recursive case now. So now we go back and we say the recursive case. Okay, solve for the subproblem if the robot goes right, add right to your solution, and then return the solution if the subproblem is solved. If not, backtrack. That means that what I first want to do is I want to add R to my solution because I'm going right. So I'm going to try going right. So solution, I'm going to append R, right, to my solution. So then let's say that I will define a variable called solution going right. So that's going to give me either nothing, right? If there's no solution, it'll give me none. Or if there is a solution, it'll give me a list of directions. So solution going to right equals to, and now I will solve it recursively. I will call solve maze helper, which is the function that I'm writing right now. And then, I might not have space. I'm gonna squeeze that a little bit. I am going to add the parameters. So maze stays constant, right? And then solution, because we appended R to the solution will be now different, okay? So we can just pass it in. And then I want to give in position row +1. Why? Because your robot is now one step to the right, right? That is the new state because you've gone right. And then position of column stays the same, right? Same thing on the y-axis. So then now we assume that this function works perfectly. So what happens if it works perfectly? Well, if we look at our maze, we know that if this happens, it's actually going to return none because it's impossible to solve the maze if you start here, right? So this is going to return none. So what would happen if it returns none? Then we would try going down instead of right. But this is not about this position. This is a general position. So we're going to write, assuming imagine in another world or another maze where going right is actually correct, then if you do have a list of something, so if it's not none, then great, you actually completed your job. Then great, you actually completed your function. Then you just return the solution that you got from this function, right? But let's pretend that going right doesn't work. Then you want to backtrack. And then we want to try going down, right? So how do we backtrack then? Well, right now, the solution has an R on it. But from your helper function or from your recursive call of the function, you know that there is no answer, right? Because if there were an answer, you would have gone, this would have been true, this would have been true, and you would have just outputted your solution. So assuming there's no answer going to the right, then you know going right shouldn't be part of the solution. So you have to remove that R, right? So you're gonna pop the R out of the solution, and then you're going to append D instead because you want to go down this time, right? And then we do the same thing. But instead we're going down. So I'm gonna define my variable solution going down, and then I'll call my function recursively again. Maze stays constant, nothing changes. The solution now has a D instead of an R, right? It has an extra D instead of an R, all right? And then position row will be +1. Oh, actually, I made a mistake here. Do you think you can find what the mistake is? When you go right, you don't go down a row. You go right, and so you go up a column. So each column is here, it's vertical, right? So if you go right, then you're actually going to the second column. So this is actually wrong. You add 1 to the column, not the row. So position row, add 1, and then position column stays the same. Yeah. So what would have happened if I swapped these? Then we would have gotten kind of like a rotated answer where every time I wrote D, it's actually R, and then every time I wrote R, it's actually D. All right, cool. So now we have going down, and then we're gonna assume that if there is a solution, then we just return the solution. Just like the same thing we did for going right. So going down. All right. However, if we tried going right and going down and there's no solution, then it's impossible. Then you backtrack again, right? Because you remember if you went here, you went to the right, and then your function doesn't know what happened previously, right? So it starts here. Let's say your function started here. Then even if you go right or down, you're not going to find a solution, right? So you're going to be outputting none, and then you're going to backtrack by removing the R on your solution. And then you'll backtrack. So how do we backtrack? We just remove the D from our solution. And then we're going to return none because it's literally impossible to solve the maze at this point. And then, yeah, that's pretty much it. What we did was we solve for the right. And if it doesn't work, we backtrack. And then we solve for the down. If it doesn't work, we backtrack and just return none. Let's try it out, shall we? So we run it. Okay. Ooh, let's see. There's an error here, line 50. Let's go to line 50. And then it says, if solution going down, if not none, syntax error. Oh, whoops, is not none. All right, we're gonna run this. Okay, I'm gonna squish it now because we are now looking at the REPL. So we have our maze, and then we could print our maze. So, oops, we're gonna use our own function to print because we wrote a better one. So then now we want to solve it. So solve maze helper. We're going to put the maze, and then the solution. What's the solution? We're going to start with an empty solution, right? Because we didn't go anywhere so far. We're at the top right position of the maze, which is 0, 0. So yeah, you're at 0, 0 because the position of the row is 0 and the position of the column is 0. And if I press enter, nothing happens. So here we see we have a bug, and then now what we're going to try to do is solve this bug. All right, so let's look at the maze helper. We're going to expand this again, and then let's try to figure out this bug together. All right, so if you haven't found it already, the bug is over here, right? And the reason why this is wrong is because we're always taking the position of the row to see where the robot is. But what you're supposed to do is to give it the position of the column for the second index. So here you take which row it is, and then you take which column. All right, let's try this out again. All right, solve maze helper, pass in the maze, pass in this empty solution and the position 0, 0. All right, awesome. Here we go. We have down, down, right, right, down, right. And that is down, right, the right answer. Aside from my terrible joke, let's print the maze and then see if this is correct. So we went down twice, down, and then right 2 times, and then down, and then right. And yes, that is correct, the answer. What if we change the maze a little bit? Let's add an X here, okay? So we run it, and then we print maze. So now we have X's here. So as you can see, we know that it's impossible to cross this maze. So let's see if the function works. Maze, empty solution, and then position 0, 0. Aha, it returns nothing because it's literally impossible to solve it. All right, what if I pass in row 2, 0, 1, 2, and column 0. So that means I'll be here on this little dot. So it's possible, right? You can go right, right, down, right. Aha, it works. Right, right, down, right. Okay, cool. So our function definitely works now. And let's put our maze back to its original position. And then now we just have to write our wrapper. So how do we write a wrapper? Well, it's actually very, very simple. A wrapper usually sanitizes the inputs of the client, and then it calls your function that you wrote that only you can use. So how do we sanitize this? Well, I mean, one thing we can do is we want to make sure the maze is an actual maze. So the length of the maze shouldn't be smaller than 1. If it's smaller than 1, it means it has no rows, right? So if it has no rows, I'm just going to return none. And then same thing, if there are 0 columns, if the size of the column or size of the row is smaller than 1, then it means there are no columns, which doesn't make any sense. So we're going to return none here also. All right. So then if everything is good, we sanitized our maze, then what we can do is we can actually just solve the maze by using solve maze helper. And then the same thing we did on the other side, we passed in the maze, we started the solution with an empty solution, and we started the position with 0, 0. So your robot will start at the top left corner. And then we press run, and now it's a lot easier to call the function. You literally just input a maze, and then you get your solution. Let's try something different. Let's add dots here, and then close off the downside. All right. So now your maze looks like this. And then if we solve the maze, then I think it's gonna give us R, 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 D, D, D. Yep, that's it. We got R, 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 D, D, D. All right, perfect. So we were able to solve this backtracking problem by using recursion. And I hope you followed along, and let me know in the comments if there are any issues of understanding how to write backtracking solution, and I'll respond to it. All right, that's it for now. And actually, that's it for all the technical part of this course. So I want you guys to congratulate yourself, and you've actually learned quite a lot just from using Python, because normally in most classes they won't teach you recursion or backtracking in these beginner courses, but I think it's pretty important to challenge our minds to try something that's a little bit more difficult with the tools that we already have, because technically we didn't learn anything new. We're still using loops, we're still using lists, and that's pretty much it. There are a lot of other data structures and syntax in Python and a lot of different things like classes and stuff that we did not teach you, but I just wanted to show you what you can do with so little. And I think that's a great exercise, is to try to do as much as you can with the little knowledge that you know. So that way you can get really creative to try to solve problems, so you don't have to always rely on other people's solutions. All right, so I think now you'll be ready for the final project, which is a Sudoku solver. All right, good luck.